Okay, hello everybody, and welcome to the February Howard Astronomical League monthly meeting. We have a really cool speaker tonight. The speaker's presentation to me seems like it's like something out of science fiction, and I'm super excited to hear about it. Before we get started with that, I've got a couple of things I was going to go through, as is our usual process here with HAL. So first things first, let's just talk about what we're going to talk about. So we'll go through some introductions. We have a few club announcements. Our speaker will talk, and then we have our regular features about shallow sky and what's going on up in space with our excellent planetary and space experts. And then we will go through some Astro members, Astro Images, and then hopefully have time to shoot the breeze. So introductions. Is anybody here new would like to say hello or introduce themselves? Any new members in the audience?
My name is Mike Frostak. I'm not new, but this is the first time I had a chance to get out in person.
Mike? Okay, welcome to the club. Welcome to the HAL meetings. Are you a longtime astronomer or amateur astronomer?
I'm an amateur. I have art, but I'm just sitting on the telescope, so here to learn.
Oh, well, great. That's the kind of, you've come to the right place, because
Right.
everybody loves to, you'll get too many people wanting to share and be excited about helping you out, and
That's
to come to some of the events. That's basically what we all do. We all just want to geek out, and we're all amateurs. This is one of the only hobbies where you proudly announce you're an amateur at the beginning of the name. Another new person?
Yeah, I'm Brian. I joined after one of the public star parties.
Okay,
I don't have anything besides binoculars. So
That's
I just show up and hopefully I can look at other people's stuff.
that's a great way to start. And yeah, for sure, you can do that. And that's how I started too, with binoculars.
I'm Bobby. Been a part of HAL for about a year, been to a few star parties, and have a telescope of my own.
Cool,
Need
excellent. Okay, anybody online want to say hello? Welcome. One more?
Yeah, I'm new too. My name's Aldous, and I went to a star party a few months ago, and I do have an astronomy degree, believe it or not, but I never used it. And now that I'm retired, I want to get back into it. And Jim was kind enough to have lunch with me today, Jim Johnson, and told me about the meeting. I wasn't paying attention to the
Cool.
website.
So yeah, well, some other time, I want to hear how you managed to go through life with a degree and not using it. But
Long story.
as long as I bet it's a fun story, yeah. Anybody online want to say hello? Okay, if not, then we'll just get ahead and get on with the meeting. So first up is our star party schedule. We have a public star party coming up in just a couple of weeks. It's so cold. It seems like it's been so long since I've been out with the weather and all that. It's kind of hard to believe it's only a couple of weeks away, but March 8th is our first public star party. Myself, Mike Krause, and Chris Todd, former club president, will be hosting and or CTOing. CTO means certified telescope operator. Basically, we'll be running the equipment inside the observatory. Usually when I show this chart, I post a couple of pictures from our recent impromptu events, but there really hasn't been any of those lately, which is okay, because it's been kind of rough out there. If the cold didn't, the clouds or the seeing have been really terrible the last month. Another announcement on my list here is that we have a new website. HAL has a brand new website. It's not live. It's probably going to go live in the next couple of weeks. And the functionality of the website, I have a feeling if you go to the website, you're probably going to want to go and look at upcoming events or some of the things that there's like a scroll wheel here thing, a carousel that shows a few things that are going on, and then the upcoming events you can click on in this column here. But there's also background information about HAL, information about the club, monthly meetings, etc. So keep an eye out for that. When we make the official announcement, I'm not sure how it's going to work. Our webmaster, new incoming webmasters are still working out whether they can bring in a secure way, bring your old, bring the hashtag or whatever, the hash codes of your old passwords from the old site. But we might ask that you log in and create a new password. But anyways, I hope that you guys will find it useful and full of good stuff. The one thing that's nice about it is it'll work really quite a lot nicer on mobile than our current website. So stand by for an announcement on that. Next thing on the agenda is Jim Johnson is going to give us a brief trip report from his winter star party.
Yeah, I went to Winter Star Party, South Key, Florida. It was. Do you have the slides? Did you get them?
No, I
Did you
didn't.
get the slides?
Did you send him an
Oh,
email?
don't worry about it.
When did you send him?
Around 11:30.
Sorry, I didn't.
Sorry. Okay, so I'll just talk about it. The Winter Star Party was Scout Key, Florida. It's about 1,250 miles from here, about 18 hours drive. So you got to really plan ahead for how you're going to get your gear down there, and maybe driving with somebody else. And 2 days sounds about right to me, what I did it in. Went from January 27th to February 2nd. The reason that you want to go to Winter Star Party, if you like going to dark sky sites, suborbital 3 sky, the temperatures are great. Highs are around 82 in the daytime. Lows are around mid 60s at night. And the sky is great, Suborbital 3, because you're in the middle of the Caribbean and the Gulf. The wind flows are laminar, so there's no turbulence. You got, even if you've got high surface winds, got great seeing. So those are the reasons to go down there. They have 2 camps. There's a Girl Scout camp and a Boy Scout camp. The Girl Scout camp was devastated by Hurricane Irma in 2017, and they really haven't restored it. There's no electricity there, so if you're going to take an RV, first of all, the Girl Scout camp is RV and tent camping, and the Boy Scout side is tent camping, and they have some glam tents over there. I'll tell you about those in a minute. But if you got an RV, you got to bring your own power, because there's none on the Girl Scout camp. It's all bring your batteries, or bring, then there's no way to charge them unless you have solar panels. Bring a low decibel generator, but it's nice and level, quite a nice place to be in February compared to what it's like up here. Porta potties on the Girl Scout side, showers are maybe 100 yards away. On the Boy Scout side, you walk over to those showers and restrooms. The glam tents on the Boy Scout side are they're like permanent tents. They have front porches, wooden floors. They have 5 sets of bunks, so 5 people are in one glam tent. So if you're going by yourself, you reserve a glam tent, you'll share it with 4 other people. Back to the Girl Scout side, there is water, potable water on the Girl Scout side. The vendors are on that side as well. The vendors, there's a food truck that provides meal service down there. Last year it was Mickey's Kitchen for the last time. This year it was Kitchen 1333, which who also did a good job, and they may or may not be back next year, so we'll see what the food service is gonna be. And we wish I had the pictures.
It's not, I'm trying to find my spam folder. It's not in my.
Okay. Who knows what I did? Trying to think of anything else off the top of my head. So it's 6 days or 6 nights. So it's not like you get down there and you turn around and come back. It's you're down there a good long time, plus the time to transit down and transit back. In past years before Irma, about 600 people would show up. The last couple of years, maybe 250 to 300 people, so still a good crowd. You're practically right on, there's like a long east-west strip. To your back is Route 1, which is now Jimmy Buffett Highway, and the front, 100 yards away is, if even that, is the water. Over to your right, to the west, and over your right shoulder is Big Pine Key. Bit of a light bubble over there, so things maybe as high as Orion, as they start to approach setting, they'll get lost in that. To the west is east is Marathon. It's like 20 miles away, so not much light from there. It's kind of small. Way in the distance, off to the right of south is you can see Havana's light bubble, but it's tiny out there. It doesn't interfere with anything. Oh, another advantage of being down there, you're 15 degrees farther south, so you can see things like Omega Centauri and Eta Carina and many, many other things that you can't see up here. Southern Cross, many, many things. One of the pictures that I sent Victor was, yes.
There's a website, astrobackyard.com, Winter Star Party, that has some pictures. I don't know if you want to be throwing that here or not, but it has like the bunks and some things there.
Has what?
It has like bunks and the setup of the camp and
Okay.
some stuff, if that helps you at all.
I'll get the, I'll publish by email the slides. It's got links to what you're talking about.
Okay.
It's Trevor Jones has that website. I met him down there last year. I didn't see him this year. So I'll get that out there. Links to,
Your slides came up.
oh, that's one of the pictures I took down there. Is this from the, this is not from the,
This is what you sent me.
okay.
It didn't come with your slide.
Okay,
It's
this is
what you
this
said.
was actually for members' photos,
Yes, yes.
but that's from down there. Kind of accessible from up here, but if from up here, it rises and sets. I spent 7 hours on this in one night. You'd never do that from up here, 7.5 hours. Anyway, so I'll publish something with the Southern Cross Astronomical Society webpage on the Winter Star Party, and I had another link. I can't remember what it was for, but I published that by email to the HAL group. And is that great, Chris? Oh my God.
You don't recognize
I
me.
didn't recognize you. Good to see you.
I was gonna say,
Yeah, I kept looking, and finally it hit me. It was good to see you.
Yeah.
So I'll get that out by email. Any questions about Winter Star Party? All right. I recommend you go. If you think about going, there's a lot of stuff to talk about. I'd be glad to help anybody out.
It was certainly one of my favorite star parties.
Yeah.
I've been 4 or 5 times now. It's awesome.
Yeah, I've been 3 times. There was, Doug Bernanke and I drove down. We were the only 2 HAL members that I know about. Last year, there was a couple more, and there's been as many as 7 to 9 down there. That's a great event. I
It's on
recommend
that
it.
front page, you just have to scroll down more, like if you go back one. And just start scrolling down and keep going, there's like ads and stuff all over, but yeah.
Yeah, there's one of the glam tents over to the right. Stop right there for a second.
Thank you.
So you see where the Route 1 sign is and the little coming downward? So that strip along there is where the RVs are parked, between that little road
This one?
and this little road right here, the RVs are parked in this area. They just got a little strip there before you're on the beach. There's the vendor area, the tents, the vendor tents and food truck and all that. Here's the Boy Scout side over here. Boy Scout side, you can, and there's the glam tents. You can pull in, drop off your gear. You have to park. I think there's parking out here now. On this side, you can, on the Girl Scout side, you can park with your gear, whether you're RVing or tent camping. There's tent camping. There's the RVs, trip along the beach. Cram tents. I think there's like 7 or 8 of them.
So I was looking for your email while you were talking, so I wasn't paying attention. Did you say that you had a lot of clear skies this year?
Okay, this year, so 6 nights, we had 4.5 good nights. That the forecast showed us. Saturday night, the last night there, the forecast just looked bad all night long. So instead of trying to break camp and pack up wet gear, we packed up our astronomy gear Saturday afternoon, and then it was clear till like well after midnight. So we could have actually had like 5 clear days out of 6, which is really good. Wind was less of a problem. I had one picture I was going to show you from last year. We had 20-mile-an-hour winds, and I had a great picture of Andromeda Nebula because the overhead aloft, the skies are so still that it's just you can do anything you want. It's got a good steady tripod. Wind's not a factor.
Is there any worry about like the wind blowing schmutz into your telescope and with the sand and the beach there?
The beach sand is actually pulverized coral, and it's kind of coarse, so it doesn't really pick up. I don't remember ever feeling any pickup. There have been cases of telescopes blowing over, so anchoring is a good idea.
Cool.
Any other
Well,
questions?
Thanks, Jim. I really appreciate it. Sorry for the snafu with the charts.
No worries, I could have helped with that.
All right, so it's too bad you saw Chris, because the next slide is get to know your board members. Chris, do you want to just say a word or two?
Yeah. For those of you who are longtime members, you may remember me. I was president back around the time that the observatory was built. But I lost my passion for astronomy for a couple of years. But then the 2024 eclipse got me excited again, and I'm back, and I'm the new observatory director. And I think in last month's meeting, Victor used the phrase, help make your club be the club you want it to be. Along those lines, get in touch with me if you want to be a certified telescope operator, because we've had a number of people who, have had changes in their lives and they've had to step away. And so we have a couple of openings, and so drop me an email at observatory@howardastro.org. Let me know how you think we should be using the observatory. I've got some ideas, but open for suggestions. So
Cool.
great to be back, and
It's great to have you back.
Welcome back.
thank you.
Yeah, you got into barbecue stuff for a while there, right?
I was into other things, other obsessions.
Okay. All right, well, great. I think maybe we'll do this. You still got time.
Yeah. Okay.
I think maybe we'll start this as a feature. We'll just like introduce one different board member every month and just have them just talk about whatever they want to talk about for a little bit. Crystal, you're next. No, you're next today, but maybe next month you'll be our board member of the month. So next is the book of the month.
So hi guys, today's book of the month is 100 Stars That Explain the Universe. So I think of all the books that I've reviewed recently, this one is surely a favorite. So just a little bit about the style of this kind of book, right? So this is not an astronomical catalog. You're not going here to look up a star or understand constellations. So it is more a wonderful narrative told in little pieces. So by choosing or selecting 100 stars in our sky, you can kind of learn more, not just about the history of its name or why we're interested in studying it, but all the interesting science that comes from finding stars in these great massive, space missions and telescopes, and learning about the human part of it too. So I think the human stories, the connections to our humanity, things like mythologies and religion and how they view these stars. But the science aspect was interesting as well, because the science is all over the place. There's so many cool things that the star is not really the centerpiece of the story. It is more the narrative path that we get to learning about different types of science. So there's things covered like stellar evolution, the birth to death of stars. There's things like better understanding nuclear fusion. You can learn about the classification of stars. You get stars that better explain how we know how far things are out in the sky, but also things like, well, we're looking at this star because there's this once in a lifetime kind of eclipse events that gave us information that we would have never had otherwise, or that we are interested in looking at these stellar systems because there's exoplanets or worlds out there that we really want to investigate and learn more about. And so this is a fantastic novel. It is super beginner friendly. It sprinkles in a good amount of the science without overwhelming you with any technical data. This is not the kind of book that's going to throw a chart at you, but it does a fantastic job of really motivating you in these little short stories of hearing the human side of why we care about the stars in the sky. So I highly recommend it. It's a fantastic book. If you're interested in checking it out, you can email me, or there's also a form online to fill out if you'd like to check it out from our library. Thank you.
Cool, thanks. I was gonna ask if that was your personal copy or do we
No,
have?
yeah, I donated to the
Ah, thank you, Crystal.
You're welcome.
Okay, so that's it for business, and now I would like to introduce Reza Ashtary, an exoplanet astronomer at Hopkins APL. Are you logged on to the Zoom meeting? So let me
Should I
stop.
share from
Yeah, actually,
my mic at all or use the mic?
the mic is actually in,
Gotcha.
in this thing, but I think
Cool.
it works pretty well. I'm
Okay.
just realizing I didn't
Sure.
enable sharing it. Hold on.
I can request.
No, I mean, I didn't, the security settings are not. You're not allowed to share. Sorry. Okay, you should be good to go now. And for the folks online, I see there's a pretty good group online. There's quite a few people. I'm gonna sit in the audience and watch the talk. So I won't be monitoring the chat. If anybody sees, if somebody would like to just sort of announce it, if there's a question in the chat and we can interrupt like that. All right. So am I still sharing?
I'm seeing Dr. Ashtary's slides.
You are, okay.
Yes, we've got his screen.
Oh, I forgot to read your bio.
Sure.
Um,
You're welcome
I-
to. Or I can just speak to it. That's fine.
Do you mind?
Yeah,
I'm
no,
sorry.
not at all. I'll
I'm all
cover
over the
that.
place
All right. Let's try to. All right, so I'll cover my background in a few slides if that's okay. But thank you, Victor, for inviting me and being patient with me. I know I was originally supposed to come a few months ago, but I appreciate you having me now. But my name is Reza Ashtary. I'm based out of the Johns Hopkins University Applied Physics Lab. Uh, so a little bit about me professionally. Our work is actually just down the street off US 29. We're on exit 15. So we're on the Laurel Columbia boundary. So we're really your neighborhood exoplanet astronomers, if you kind of think about it. But
Friendly neighbor.
no, yeah, definitely friendly. You'll often see me working out of like Ragamuffins coffee shop in Laurel, or just random coffee shops around. I have the luxury of being a hybrid employee and working at Johns Hopkins and at home with my wife all the time. But I think I have one of the best jobs in the world. I honestly think I'm in the top 1% of happiest people at their job. I get to work on things like studying exoplanet atmospheres, uh, also using radio astronomy, their magnetospheres as well, and measuring their magnetic fields. I have a background in working for or designing deep space communication systems for the Dragonfly mission that's supposed to go out. Some concepts for a Voyager follow-up called Interstellar Probe. So I'm well versed in radio communications as well. So I've written papers on things spanning technosignatures to observations with Hubble and JWST for atmospheres, and yeah, I actually started out in engineering, so I I'm very fond of being able to build the toys before playing with them as well, and having that understanding on both sides. And lately, everything's been trending towards AI-based things, so I'll cover that today in a little bit. But in terms of what I actively work on, it's a mix of those things. Oh, oops. So outside of work, I'm a husband to my wife, who's here, the beautiful lady in the front, and in the photos of us, luckily getting to go to Italy for work, and taking some nice photos there. And then the main star of the show is our dog, Teddy. He's a little fox and rascal, but love him to death. And unfortunately, I'm a Man United soccer fan. It's been rough, but I'm loyal. And yeah, recently we've gotten into snowboarding and skiing, so it's been nice to do that. So, I'm an exoplanet astronomer. For some of you, you may not have heard that word before, but an exoplanet is a planet orbiting another star. As of today, we have almost 6,000 exoplanets that have been confirmed, and we have plenty more if you include the candidates that we haven't done follow-up observations to confirm yet. Some notable work suggested that for each star, there's at least one planet in the Milky Way. So that's pretty optimistic in terms of planet hunting. In terms of their diversity, about 20% of the stars like our sun are predicted to have an Earth-sized planet in its habitable zone. But importantly, please, please, please remember this. If it's in the habitable zone, that doesn't mean it's habitable. It doesn't mean there's life on it. That just means the initial conditions might be right. So there's a lot of factors that go into that recipe for life and habitability. So whenever we want to start talking about the different types of planets, one of the main ways that we categorize them is by radius or size. And as a quick primer, here's a comparison of the, I guess, units of measure or benchmarks that we often refer to when we talk about exoplanets. We usually refer to a lot of them in terms of Jupiter size or radius, also Earth. And to scale, this kind of gives you a sense of how much bigger each one is than the other. And then the other metric that we use is mass. So Jupiter, again, is obviously the biggest, but the next categories that we often refer to are Neptunes and Earths. So you'll hear me refer to exoplanets as hot Jupiters or sub-Neptunes or super Earths, and I'll get to that more in the future. But For now, keep these in mind for radius and mass. All right, should have brought my water up here. But actually, yeah, let me grab my water. Okay, so we have three primary methods of detecting exoplanets. These aren't the only ways, but these are definitely the most successful ways in terms of planet hunting. So on the left, you see transits. Every time a star passes, or sorry, a planet passes in front of its star, you'll see the amount of light that we can measure from it dip down as a function of time, shown here on the x-axis. And so as it orbits, you'll see that radius that we measure correspond to how long that dip in light lasts for. And that lets you know about how wide the planet is. And then that also gives you a sense of how much of the starlight is supposed to get blocked. So we actually get a few characteristics from the orbits of these planets just by measuring it as it flies past in front of its star. So the next method that was very popular in the early days of exoplanet hunting is radial velocity. And that generally measures the mass of each exoplanet. And, excuse me. That works primarily by measuring the Doppler effect. So kind of whenever you hear an ambulance come and go and it gets higher pitched and then lower pitched as it's passing you and leaving, whenever we measure the starlight from that star, as it wobbles towards you, it's going to get higher pitched or higher frequency. And the wavelength that you measure is going to get more compressed and it's going to turn bluer. And then as it's starting to shift and go away from you, it turns more red as a consequence of it going away from you. So if there's a big enough exoplanet orbiting that star, it's going to basically play a little radial tug of war with its star, and you can do the math and figure out how big of an exoplanet that must be, or how massive is that planet to make that star wobble or show that much Doppler. So that was the radial velocity method, or RV method, that you might hear. And then, of course, there's direct imaging with just honking telescope diameters and angular resolution and incredible detectors, in addition to some advanced optics for blocking out the starlight, whether it's a coronagraph or maybe in the future a star shade. You can actually image the planets, especially for these face-on cases, not like the transiting cases, but for these orthogonal facing systems where you can actually see it almost flat orbiting its star. Here's a case for that where I believe this is from the Subaru telescope in Hawaii. And you can see 4 or maybe even 5 planets orbiting this star. So really pretty incredible and so mesmerizing. So how does this look to date? My coworker put together this neat video on a year-by-year basis, and then you see in the beginning it was the RV method being used to detect what was mostly Jupiter-sized planets or bigger, but these planets are actually much hotter than Jupiter for the most part. So here's a little infographic with stickers showing where our own solar system planets lie compared to the exoplanets that we've detected. And you can see, first of all, that blue dominates everything, almost. So since transit detection has come out, The Kepler mission and the TESS mission have detected exoplanets at not only a different demographic than what was being found previously, but the rate at which we're detecting planets now is just much, much higher. So that's why we're getting close to that 6,000 mark for number of exoplanets that we found so far. So the terms that you might hear, there's a big diversity in the types of planets that exist out there that we found so far. So you'll find a large amount of them in this upper left quadrant where they orbit much faster. So the year on most of these is only 2 or 3 days. So these are Jupiter-sized planets orbiting very, very close to their star, closer than Mercury does in our solar system. But they orbit their stars in 3 days. And so we call them hot Jupiters. And so spanning to the right, very clever with the naming, you might hear them call it warm Jupiters if it's further out and it takes longer to orbit that star. But then going down, you hear the two phrases that I used earlier. So you'll have sub-Neptunes, planets that are roughly but slightly smaller than the size and the radius of Neptune, and then you have super Earths. But we haven't quite found too many planets just like Earth yet. And there's also a different technique that I haven't spoken to as much called microlensing. That happens whenever a star with exoplanets is in the background of a star in the foreground, kind of like whenever you're driving on the road and you see the trees that are closer to you passing by much faster than the trees that are further away from you. That parallax effect is what it's called. As those stars in between you and the background ones pass by, the gravity is so strong of that system that it'll magnify whatever happens to be passing behind it. And you'll see the spike in light, and that lets you get a temporary magnification of what's behind those stars or passing behind those nearby stars. But the number of detections that we have from those, as you can see by these darker circles, is pretty minimal. So since most of my life revolves around exoplanet transits, that's what I'll be focusing on today. And we already spoke to this, but you'll see as the planet passes in front of its star, we call this a transit. And then as the planet then eventually reaches behind the star and eclipses it, we call that a secondary eclipse. So if you hear me use the two phrases transit or secondary eclipse, that's what I'm talking about. So how do we do science with it? Well, the amount of starlight that's blocked, or how deep that transit appears, how deep or shallow this appears, corresponds to planet radius, as I mentioned before. And so we'll take the ratio of the radius of that planet compared to the ratio of, or the radius of that star, and we can back out about how much we expect to see that flux reduce. So that lets us know how much the light is going to drop. And then we can also do some math on that, making some assumptions on the gravity and makeup of that planet to estimate about how high what we're measuring in those atmospheres appears. And so how that plays out in a simplistic analogy is we have two different categories of planets. We have bigger gas planets, like in our own solar system, and relative to their size, they have smaller cores, but a lot of gas volume. And then on the left side, you have larger core planets with higher gravity, with these more compressed atmospheres that are, yeah, fun to work with. So you can guess which one is easier to measure. The one of that one, yeah.
What causes the dip when it goes behind?
So whenever it goes behind the star, if you'll keep your eye here in this animation just on the orange, you'll see the amount of the reflected light on the planet. And so when the planet moves behind the star, you're losing the little bit of reflected light that you were getting in combination with the starlight itself. And so that, you can imagine if there was no planet here, not, aside from just not having any transits here or eclipses, it would be almost a flat line because there's no sinusoid variation that's being created from an oscillating reflection. Yeah. So no oscillation from the brightness of the planet, no oscillation in this light curve. So, again, in a simplistic format, how we always think about this is a planet has a core, probably. Planet formation is still an ongoing deep research field. So how planets form and what their interiors are made of is still up in the air for the most part, really, until we, I guess, make a spacecraft that can dig into other planets or perform ground-based radar. But for our case, we study exoplanet atmospheres. So the combination of this atmospheric envelope full of gases with a core and the gravity and all the physics that goes on between them is what we study. And so one great analogy that one of my mentors shared in the past that I shamelessly stole from her was this really cool example of Earth's atmosphere as seen from space. And so we're trying to measure the depth of our thin blue atmosphere, right? And we want to do that across a different set of wavelengths. So we see the molecular makeup of that. And what I say, what I mean when I say that is at different wavelengths, our atmosphere looks different. So in the infrared, as you go more and more towards the infrared, you'll see the atmosphere becomes more transparent. There's less scatter, and there's, yeah, whenever there's less scatter, it's easier for the light to travel through it. And if it's transparent and there is a gas, then you can definitely measure it a lot easier. And the more you go into the infrared, the easier it becomes to detect those molecules as well. So here's an example of ozone in the Earth's atmosphere compared to just an arbitrary band where there's not much. But the difference you see in just one filter from the other is crazy.
Is that real data or notional?
I don't know, but I'm sure if you look this up, it might tell you. But I wouldn't be surprised either way. Yeah. So again, what we're trying to study here is as starlight passes through not this close-up case, but a very, very hundreds of light years away case of starlight passing through the atmosphere of a planet right before and after those transits, on the edges of those transits, and even throughout it. What we want to do is take that starlight and its colors that are coming through across all these different wavelengths. And then as it travels through certain gases, we know the emission lines for how gases, or how they emit in terms of wavelength and intensity. And so we can back this out using physical models to see what gases then we know for sure exist whenever what we analyze what we measure here on the far right, which is after it passes through that gas in its atmosphere, the missing bands are what we call provide what we call a transmission spectrum. So here you have an emission spectrum, here you have an absorption spectrum, and then finally, that emission plus absorption gives you a transmission spectrum, is what we call it. And what that looks like is, here's an animation that a student at JHU created. And you can see in the top left here, as the different wavelengths pan from blue to red light, you can see the different features and widths of this planet vary. And so you'll see these flashes of it all of a sudden getting very diffuse and wide. And that corresponds to these peaks that we measure at those colors. So here, hypothetically, we added some sodium, potassium, and water, and the corresponding sizes that you would expect for the atmosphere as it passes in front of the star would look like this. So you've been through a lot. Probably kind of like drinking water from a fire hose at this point. It's not going to get any easier. So let me drink a little bit of water, and then we'll talk about how this all looks in practicality or in practice. So here is an image downloaded from JWST. What you're seeing here is basically an image from our spectrograph instrument. So in a very simplistic form, we've taken white light from our telescope. We've put it through a prism or grating that then converts that white light to color. And then this smear is this. So that's our transmission spectrum, but there's a lot of work to do on it still from here. So these are almost raw images. And so we need to take these raw images and turn it into useful science. So our star was about here, and this was a slitted instrument. So there's actually a slit right around there that then creates this smeared spectrum across our detector. So then we have hundreds and hundreds of these images that then we have to treat for the noise that we don't want. Sometimes there's background stars. Most of these little pixels that have been taken out have just been because the instrument is the detector is so sensitive that any unwanted light might cause them to illuminate just unwantingly. So often we'll have to post-process like this and clean up the data. And so we started with this, and now we have this beautiful, clean data to just work with. Yes.
How much does dust in a solar system believe to create noise? I mean, you've got light scattering, or say it's a newer solar system, presumably with more dust in it. How much would that interfere with your measurements?
So we tend to not look at young stellar systems that are still pretty dusty and haven't pulled that dust in to form planets because it's so noisy and it'll, yeah, it won't make a clear observable transit. But usually what they do for those is they'll go a little bit longer wavelength than into radio, and using large ground-based radio observatories, or even sometimes JWST, and do planet formation studies in those younger systems. So, but for here, we took this raw data that we were starting with. We did some signal processing on it. And we got this beautifully cleaned image. And so we do this for hundreds and hundreds of those images for different times, consecutive times. And so each one of those images from before has now been turned into one of these dots. And what you can see is obviously there's a planet passing in front of a star. And yeah, every time I see one right after we have data come down, it's just the biggest sigh of relief. It means nothing messed up, everything pointed the way it should, the instruments behaved properly. You didn't get something cruddy and unusable. So what that then looks, oh, please go ahead.
Is it often there'll be more than one planet, and how does that affect the output of this, or is it,
So we usually know how many planets are going to be in that star system that we're looking at beforehand. JWST isn't necessarily a planet hunter. It's more for following up the transits that have been detected with the smaller telescopes like TESS or Kepler. And then if we think there's a compelling enough case to actually measure its atmosphere or do some other science with it, then they'll ask for just enough time to measure at least that one planet. If you can make a good enough case to measure multiple planets in the star system, like the TRAPPIST-1 system that you might hear about every now and then, there's multiple Earth-sized planets in that system. In the rare cases that does come across, you'll see an eclipse on or a transit on top of a transit. And but yeah, those are called planet-planet occultations. So yeah, that's a whole different rabbit hole. But they do come across, especially in those family style systems, if you will. So, but what we were looking at here to the left originally was the white light. So if we then look at that across a bunch of different wavelengths, so here from top to bottom, we're showing more infrared as we go down. But the color represented here just shows the amount of light. So as you see the color here transition to blue, that means there's less light. And so it's just another way of showing this data across a bunch of different colors of light. And it also lets us know that our detector was detecting the transit and across all of the different wavelengths that we're interested in. Yes.
Do you take out the red shift and just leave it in there?
There's not a ton of redshift for these because that's more for galaxies that are very far away. These stars that we're looking at, usually they're only it's funny, I see only a couple hundred light years away. But galaxies are so much further away that then redshift becomes a more serious issue. And also, if there was even any minimal redshift for us, it'd be kind of applied equally to everything. You would definitely care about that more and for a Doppler style measurement, like radial velocity measurements. So one thing to remember, and this is crucial for how we tie in AI in the future, is remember this MAD metric. So it stands for mean absolute deviation. And what that means is how much your data points scatter. So if you had a really noisy observation, you could imagine these would be all over the place and everything would get fuzzier and it'd be hard to see. And some of you could remember that by thinking of Mad TV or Mad Magazine. For me, I always personified with the depressed Persian tow truck driver skit they had, so I always thought about that. But however you remember it, just remember Mad. So we then break up this color data into a usable number of channels. So we then create color channels for ourselves. And we guess about the right size and tilt and distance from its star for each planet. And we try to fit our guesses, which are shown here in black lines, to the data that existed originally. So how well it agrees is shown in the bottom. So it looks like it agrees almost like a flat line. So that's pretty good. If it didn't agree well, you'd see these data points stray away from this black line. So this is a case for everything being nominal. Then we do that across all of those channels that we originally looked at here. And that gives us an estimate for each one of these data points is an estimate for at which color of light, how big does that atmosphere appear on that planet. So we've now created a spectrum of planet's atmosphere. And you can probably see there's some obvious things.
So is that only along the parts where it's dipping down or rising up? Or is it through the whole time?
So those are the most important parts. Here is called an ingress. I'll go back a lot, I guess. Yeah. So here, right as it's passing and leaving, those are called ingress and egress.
When only the
And
atmosphere is.
Yeah, so it's a pure atmospheric measurement there, but the rest of it still also plays in, but most significantly there. Like 90% of the atmosphere that we see comes from those pure atmospheric parts. But the core of the planet, though, how just the strict diameter measurement of it plays in a lot as well. So we have this beautiful spectrum that we've created from these tens and tens and tens of light curves that we've fitted for every color. And we are getting some science out of it now. We have, for this instrument at least, the data from about 2.7 microns to about 5.3 microns. So our spectrograph created that wavelength range, and we got this data out of it. And please don't share this or screenshot it, but two of the features that are pretty obvious that you might be able to see are the CO2 bump on the far right side of it. And so that's carbon dioxide in the atmosphere of this planet that is extending to the right. You can see about almost 2 scale heights is what we call it. So about 2 times, say, 650. So about 1,300 kilometers up its atmosphere, you see CO2 extending out there. And so a little bit further down, you also see water predominantly in its atmosphere. And so from about 150 light years away in this case, we've detected water and CO2 in this planet's atmosphere, or actually over the past month. So this is fun. And yeah, please don't share this material yet. So how does AI processing work in with all of this? so the process that we just stepped through, as you could imagine, gets to be pretty tedious. We did a high level overview of all of it, and there was still a lot of knobs to turn to get everything to fit. But this was presented to me about a year and a half ago, and a professor at Johns Hopkins by the name of David Singh, who's a rock star in the field, had a contract for Hubble to analyze atmospheres for, he originally wanted about 100 planets. We eventually argued our way down to about 43. And still, just to get the spectrum for each one of these planets usually takes a professional astronomer about 2 to 3 weeks. There's, throughout this data processing pipeline, there's so many things that can be tweaked, and if you do it wrong, it might show you a false signature of something in an atmosphere, so you have to be very careful, and it was very nuanced, to say the least. And so we had the task of doing this for tens and tens and tens of planets, and basically we had to figure out an automated way to control these knobs, which were just all over the place, uncontrollable. And a big problem that we had was we couldn't use a traditional machine learning approach or AI system to that required data sets to train it on, or like a classifier to tell it, no, this is what you want to do, this is what you don't want to do. Every telescope observation, especially a space telescope observation, is like a snowflake, and the star that it's pointing at is going to be completely different than the next star, even if it's a little bit brighter. How your detector and the pixels on it react is going to be completely different. How much heat it builds up in your system will affect the performance. So you want to get that thermal noise stable. There's a lot that goes into it, but long story short, you don't have this luxurious stockpile of data to train an AI system on. So we had to develop an algorithm that was intelligent enough to make these smart decisions that created beautiful light curves and spectrum for us. And so I've shown a few of just the names that we have for these parameters that we control, but all in all, there's about 20 to 30 that you need to control. And this usually required a professional astronomer or data scientist to sit there, run this on the computer, rerun it and rerun it and rerun it and rerun it 100 times until they saw the data cleaning up, and eventually it looked less scattered, and it started actually resembling something like transit. And how we train all this on was using that metric that I mentioned before, the MAD value. And so feeding in this MAD value to assess the fitness of how well this AI program was making these decisions was really one of the key things as well. And we took the same approach that astronomers traditionally have, and they took a sequential optimization approach. If we want to dive into the AI theory later, I have some backup slides, but we also developed genetic algorithms and parametric sweeps and different types of intelligent optimizers to find these best solutions. But we ended up going with a parametric sweep where you find the best values for each of these knobs in almost a sequential manner. And we did this for all of the planets that we were assigned, and we turned this tedious 2 to 3 week process into a one-click process that takes 1 to 2 days. And so here's an example shown where this is a pretty typical example. Here you see some noise and fuzziness in the middle of this 2D plot, at least on the bottom. And you see to the right, it looks a good bit cleaner. And up here, you see the MAD value for that white light curve. This looks a little bit different than what you were seeing before, where it was a nice continuous line, because this is Hubble data instead of James Webb data. Hubble orbits the Earth as it takes its measurements. So you'll see here it was orbiting and it was in about the right spot, and it was taking our measurements for us. And then because it orbits the Earth about 11 or 12 times a day, it then went behind the Earth, and we had to wait again. Then we started taking our measurements again, and it was not made for exoplanet science, but scientists much wiser than I have come up with hacks to make it work. And you can see these little like ramp ups and all these effects that you'd ideally not have, that we really had to just model out. And so there was a lot of post-processing that needed to be done to make Hubble work for exoplanet atmospheres, but we made it work. And we tested our AI-based system for a set of exoplanets, and on average, we saw almost a 30 to 40% improvement in the results that we were seeing, compared to already our best guesses for how to create high-quality data. And we had 6 cases where we had direct comparisons to experts in the field, and the AI system created more accurate and precise data every time. So that was pretty awesome. So the science that we got to do is we created these transmission spectrum for a much shorter wavelength than what I showed before for JWST. But for the Hubble WIFC-3 instrument specifically, the wide field camera 3, we had these measurements that we created for each planet, and we highlighted 2 bands in its spectrum. So the very well-known 1.4 micron H2O band, where water typically should appear if it exists or is observable in an atmosphere. And then the J band, which is typically a very unremarkable, featureless band. So by comparing these two, we get a sense of, in the atmosphere of this planet, about how much water resides in it. So we did this for a bunch of planets, and each one of those water measurements is then shown here for each planet as a dot. And so each one of those spectrum or atmosphere spectrum is shown here as a data point on this plot. And you can see these filled in regions are from a very notable paper, where one of the best model agreements that we've had to date for tying a uniform model that applies equally to all gas and Neptune-like planets. And you can see that we got a pretty good agreement with what they had for their model. And here we try to show the 2 different categories of planets that we were looking at. So for the iron-colored red brownish dots, those are more like Jupiters and Saturns. And then the more Neptune-like and super-Earth planets, really just sub-Neptunes, not so much super-Earths here, are shown in blue. And so you see that makes sense. On the x-axis, we're showing temperature here. So as you get colder, you see more of these Neptune-like planets popping up, and there's certain points where their atmospheres become pretty noticeable. This wasn't anything new or novel, but this was a very good agreement that we got for our study that really backed up how we think planets and their atmospheres develop. Then the really fun part is we discovered this new demographic where we took that same data, and here the amount of water in the atmosphere of the planets is shown in color. So the bluer the dot, the more water in the atmosphere. And we noticed this trend that spanned pretty much from hot Jupiters down to these colder sub-Neptunes, that there's in this region that we call the clear sky corridor, there's nothing but successful observations of these planets' atmospheres and what's in them. And so this is now super exciting for the opportunities with JWST coming out, for us to really have this guaranteed window of exoplanets where we can study and know we're going to get good ideas and measurements for what they're made of. So that's super exciting. And as we develop, as we continue these studies with JWST, we're going to see what we get to unveil. But the reason we think this exists is because what's happening is at these hotter temperatures, it's so hot that you're getting salts and metals and silicates that on Earth we typically think of as solid. It's getting so hot that they're turning into gases, and they're creating clouds in the atmospheres of these planets. So you'll see liquid iron in the atmospheres raining down on a lot of these planets, or diamonds falling from the atmospheres of these planets. It's so hot that things that you don't associate with rain or think of as solids just don't exist like that. And then on the other hand, as we get colder here, we start to see more haze appearing in these other atmospheres, and that's why we think we can't see into them. But this is kind of the bee's knees for our field right now in terms of our understanding of why different types of planets behave the way they do. So what's next? We recently launched JWST in the last few years, and you can see just size-wise, it's a big upgrade from Hubble. So it's much more sensitive, but in addition to being much more sensitive, technology for the instruments has gotten much better at cooling everything down, getting rid of that thermal noise or any heat that would cause any unwanted noise in those infrared bands that are really focused on heat. So the technology is finally here where we're being able to progress our study with what we were seeing with Hubble, shown here, to the more infrared part of Hubble using WIFC3, what I showed for my study, to then now with JWST. And in addition to providing more sensitive instruments, you can see just in the infrared with the atmospheres being more transparent, it being easier to measure these little bits of the gases that exists in these atmospheres. We're really getting to understand the different, more complicated processes of how these planets work. If there's SO2 or CO in these atmospheres, then that's a sign of photochemistry. We're starting to understand how sunlight can be turned into energy on these planets and possibly used towards other processes. And now with JWST, because it's a bigger telescope, we're able to finally study smaller planets as well, and that includes more Earth-like planets. So what we've learned here for the from Hubble, especially the past few years, we're now starting to translate that into honing down a good understanding for what Earth-like planets and Earth-sized planets also should behave like. And we're starting to get a good idea, or at least a better idea, of where to search for life. So that's what I wanted to cover today. In summary, we created an AI-based process that now took telescope processing down from 2 to 3 weeks for the most state-of-the-art telescopes down to 1 to 2 days. For a typical mission that lasts about 10 years and observes a few times a week. This amounts to about 35 staff years or years of salary that we save. So that's a good bit of money. And yeah, with JWST, this is going to be so much fun in the future. We can't even comprehend what we're going to discover yet. So it's been a whirlwind, and I'm so lucky to be one of the people that's stuck in it. So, yeah.
Looking at quantum computing here also to help with these calculations.
I am not the person to ask
Oh.
about quantum computing. Fine. Yeah.
I don't fully understand how Hubble works. So like when you have the weeks or days of access, are you like the exclusive? Do you have your team have exclusive access to it, or is it kind of time shared
It's time
between
shared.
many
For
missions and all?
scheduling the observations.
Yeah.
It's time shared, and there's a tool that Space Telescope is known for. Its acronym is APT, the Astronomer's Proposal Tool. So it's all done with that, and that performs all of the scheduling. So if there's other astronomers trying to take observations, they'll plan accordingly to like when would be the right time to look at it and all that.
So all the knobs is really just configuration is sent with your request to wherever, wherever, and then you get the results back.
Yeah, so we have to tell them how to set up the detector, how many frames per group and integration, and how long, and if we're gonna do a transit observation or a different type of observation. There's a lot of different, especially with JWST, there's a lot of different instruments to choose from, and each of them you need to know. You would first simulate it online how it would act before you submit how you're going to perform it on the telescope, right? And a lot of times nowadays we have to include that with our proposal to show them that we're not going to point this $12 billion telescope at the sun. So, yeah.
There's an
Yeah.
online question from Harini.
Go
Okay.
ahead, Harini.
How do you know which star is which, and how can you observe each one without observing it again and again?
I don't think I heard this last part of your question, but I can answer at least the first part, and then you can follow up if that's okay. So we know which star is which because we've had other telescopes in the past, and a very well-known one recently called Gaia that focuses on just studying and observing stars and even finding new stars. And so that performs these surveys of the sky and catalogs what type of star it is, how bright it is, its motion, and its location. And then using these databases that are then made public online for us to use or find and search through, we then choose those stars and put it into the computer programs for Hubble and James Webb using this APT software that I just mentioned. So that's how we know which star to look at.
And what was the second part of your question, Harini?
The second question is how can you observe them without observing the same one over and over again?
So do you mean the same transit over and over again?
Yeah.
So a lot of times we actually need to observe that transit over and over again, especially if it's a planet with a smaller atmosphere, like an Earth-like planet. So it's easier for us to see a huge planet with a huge atmosphere, a puffy atmosphere especially, pass in front of its star, especially with James Webb. And a lot of times, just one of those transits is enough for us to get a great idea of what's in its atmosphere. But if it's a trickier, more compressed, higher gravity planet where everything gets sucked in towards its core, or if it's cloudy, then we definitely want as many of those transits as we can measure, because then we have a better guess, a more certain guess of what we are seeing in its atmosphere. Okay, yeah.
So if you observe one of these transits and you get the spectra and there's no difference, you reasonably conclude that it's a rocky planet with no atmosphere?
So a flat spectrum.
Yes.
Is what you're talking about.
Where basically the transmission spectrum doesn't look any different from the solar spectrum.
So yeah, so in those cases, what we do is we compare it to what we call a black body model. So it's just pure heat being absorbed and then dissipated. No dynamics with it shaking hands with atmosphere or anything like that. But this is a huge, huge problem that's coming up right now with JWST because we're starting to push JWST to study these smaller planets, what we call rocky or terrestrial planets. And the ways that we are trying to advance that is for every time we see a flat spectrum that looks like there's nothing there, even though our intuition tells us that there should be something there, is we first model how it would look like if there's clouds all over the planet. You could imagine if there's clouds covering a planet, they might reflect a good bit. If they're whiter clouds or grayer clouds, that'll affect how much light you're measuring. So these are a lot more tiny of differences and subtle of differences to pick out compared to what I showed earlier, where it was a nice big bump and you knew there was carbon dioxide there. Clouds are much more wiggly between them. So a lot less definitive. But then the other thing that we can do is we can look at the secondary eclipse, what I was measuring, or what I was mentioning before. So not as the star is passing in front of its planet. Oh my goodness. As it's passing, oh my goodness. Okay. As it's passing behind the planet, those moments where it's starting to pass behind it, we can measure the combination of reflected light and emitted light from it. So when it's completely behind it, then you know whatever differences that you're measuring aren't from the star, they're from whatever heat or light is just being given off by the planet itself. And so we then create, instead of a transmission spectrum, what I've shown here, just an emission spectrum of the planet. And so a lot of times we'll compare that spectrum that we see in the transit to what we see in the eclipse behind it. And we'll see that there is some like big differences in chemistry. Maybe when it's going from night to day, there's this huge circulation of clouds that we see in a lot of cases, because especially for these planets that we observe where they're close to their stars, they're not spinning. They're like the moon is to us, they're tidally locked. And so really the only time you get a nighttime and a daytime is in the year of that planet, like what's shown here. So as the planet swings from day side to night side, you'll get a lot of times it's hundreds and hundreds of degrees of difference. And what gases can exist, what liquids can exist is going to completely vary. So that's where we are with that. And that's really kind of the cutting edge of what we're able to do with James Webb now. So we're starting to understand how the atmospheres of these trickier, smaller planets behave. So yeah, Victor.
Are there certain chemical compounds that are acknowledged to be like biosignatures?
Yeah.
And are you able to, do you have instruments that can measure at those wavelengths where you expect to see them?
Yeah, so that's not my focus, but that definitely is something that we look for. I mentioned the different altitudes that you can back out of these measurements. So you can see kind of how high up in the atmosphere water was showing up here versus the carbon dioxide. There's a lot of gases and molecules that shouldn't appear at the same areas of the planet unless there's signs of life. For Earth, an example of that would be water in the atmosphere and methane in the atmosphere. That won't really happen unless there's some sort of like crazy activity happening in like a similar ecosystem. Because if a planet naturally produced both, that it shouldn't coexist. Like the chemistry shouldn't work out for that, at least for a rocky. So there's stuff like that to pick out. There's a lot of false, misinformed papers out there that'll say, oh, this planet, we've detected a biosignature on it. Nothing's been backed up yet. There was one case of a very well-known planet called K218b. And they saw basically one of these bumps go not even as high as what's shown here. And it was a bit of a reach, and they said, oh, we found a sign of life. And no, every other astronomer in the field was just like face palming so hard and trying to say like, oh, please don't start this. It's going to discredit everybody. And it's made everybody definitely hanker down and be a lot more pragmatic with what we're declaring we're finding. So
Any other questions? Well, I would like to, were you done? Was there anything else?
no, that was it.
So thank you so much. Really cool.
Thank you.
It's super exciting too. I mean, you can see what you're saying about being excited about your job.
Oh yeah, it's I mean, my wife knows. I'm always
So, yeah, if you can, it looks like, can you stick around a little bit? We might have some more questions at the end of the meeting. I'd like to once again say thank you to Reza, and really appreciate you coming out and giving us very clear and cool presentation. So I'll move on with the rest of the meeting. So the next item is our Shallow Skies section with Jim Tomney. Jim, are you there?
I'm here. All right, so basically, let's run through the planets. Mercury, between now and our next meeting, this is going to be really well positioned at the end of the first week of March. It's going to be in the evening sky. So this is going to be a great opportunity to catch our smallest planet. Next. Venus right now, very prominent, but it's going to drop like a rock, and it's going to head for a inferior solar conjunction March 22nd. So over the next 30 days, even if you have a small telescope, you'll be able to see it change phase and grow in size. And there was somebody in the audience tonight talking about binoculars. Right now is a good time, that really bright star in the western sky. Take your binoculars and focus on it, because you'll begin to see it appear as a crescent. And that's kind of cool to see in your binoculars. Next.
The person who said that just happened to step out to go to the restroom, but I'll mention it to him when he comes back.
All right. So Mars is still pretty reasonably observable. It's at 12 arc seconds, but we're pulling away pretty quickly from its January opposition. It's going to go down to 9.5. Usually, once you dip below 10 arc seconds, it's a little hard to do any sort of visual observing. But the northern polar cap right now is quickly beginning to disappear. It's being warmed and gradually sublimating away. So if you kind of take a look at it recently and you see how big it is, it'll disappear pretty quickly over the next 30 to 60 days. Jupiter is really well positioned, very high in the sky in Taurus, and it's very active right now. There are eruptions in its north tropical zone that everybody's been kind of buzzing about. And there's always something cool going on Jupiter, so that's a great target. Saturn is pretty much gone for us for a few months until it reappears and after solar conjunction. So we probably won't be talking much about Saturn until later in the spring. Next.
Hey, Jim, I have a question about Venus.
Yes.
I can't remember a period of time, or maybe it's just because I'm more tuned into this sort of thing these days, but it seems like it's been super high and super prominent in the sky for a long time this last couple of months. Is this just like some special event or just
Well, it's basically kind of related to how our ecliptic lines up in the springtime sky. Right around, I think, like March or April, the ecliptic, when it is on the western horizon at sunset, is its most vertical. So the distance of the planet away from the sun, its elongation, translates into almost vertical height. I think it was actually a little bit better. It was either the last apparition or the one before. It actually was not setting until midnight. That's how high it was.
Wow.
So, but at any rate, yes, you're right. It is because of the time of the year that this is happening. It's pretty darn high.
Yeah. Okay, thanks.
So the next slide.
Sorry.
All right, so let's talk a little bit about Mercury. Again, this is just what I was talking about with Victor, is because of the inclination of our ecliptic, you're getting the best height into a mid-northern latitude view of Mercury. This is from Sky and Telescope, but this really kind of points it out. In October, the ecliptic is much more on its side, as you can see on the left there. So even though Mercury is the same distance, it's hardly high in our sky at all. Compare that to what we're going to get this month coming up. It's that distance from the sun translates into a much higher position in our sky because of this positioning of the ecliptic relative to our horizon. And this is why springtime apparitions or evening apparitions of Mercury are the best. It's your best chance to see the planet. Next click.
Thanks for this diagram. That helps me a lot.
So it's going to be visible soon after sunset from about March 1st to the 13th, with the nights of the 7th and the 8th as your very best opportunities. That's where it's going to have its greatest elongation. And if you get it in a telescope, it'll look kind of like a quarter moon sort of appearance. All right, let's go one more slide. Of course, the big thing coming up is going to be our lunar eclipse on the night of the 13th and the 14th. It kicks off just before midnight for us with the penumbral, which you really have a hard time seeing. It's interesting that actually photographs tend to kind of show up the penumbral a little bit better. But the real visual part of it will start at a little after 1 o'clock, full eclipse at 2:26, maximum at 2:58, and then the eclipse ends at 3:31. A long time in the full shadow, and that's because the moon is going to be at apogee, which means it's at its farthest point from the Earth. So it'll be smaller and moving a little bit slower through the Earth's shadow. And so this should be, weather permitting, a really nice eclipse. The only downside is that it's going to be early in the morning. Next. So what could you do during an eclipse? One of the things is to estimate how dark it is. So, during the maximum eclipse part, and you can do this with your naked eye, or you can actually sometimes use binoculars and reverse them, look through the large aperture to kind of make the moon look more pinpoint and estimate how bright it is. And actually, Sky and Telescope had an article that there's a researcher who actually would love to get your estimates for the Danjon scale, your Danjon rating on this lunar eclipse next month. So you can reference Sky and Telescope to send in your observation to him if you wish. Another activity, if you'll click again, Victor, is crater timings. And what this amounts to is you watch the shadow gradually creeping up on a known crater, like Copernicus or Aristarchus or Tycho. And the moment that it touches the rim of that crater, you note the time. And this can be of some scientific value as well, because the atmosphere of the Earth kind of shrinks and swells and back and forth. So this gives data as to how large the atmosphere was when it first touched that crater. So again, that's kind of like a fun thing to be doing while you're watching the eclipse partial phase heading towards totality. And I think that is it. Yep.
Yeah, thanks. Next up is Wayne, but Wayne, your charts are awesome, but I don't know if, can we defer them for another meeting, next meeting?
Yeah, sure.
Yeah, I think we're kind of.
Yeah,
running out-
it would be tight.
Yeah.
I don't know what else you have left. I don't know how many images you have.
Not that many, but I also want to not leave the nature center too late. And I want some time to talk to Reza.
Yeah, no, it's fine. Go ahead.
So, all right, I'm just gonna skip through your slides. Everybody, don't look. I need one of those little camera, those no camera things.
Any questions?
Do you realize, Victor, this is being recorded? You can go back later and pause.
That's one of the things I want to talk to Reza about, because
Yes.
I'm actually gonna edit because we post these on YouTube, but I wanted to talk to you about this after the meeting, because I'll edit out the no picture slide.
Oh, that'd be nice.
Yeah, it sounds like you're going to publish that soon, or hopefully, or, okay. Okay, so next we're gonna just go through some, thanks for understanding, Wayne. Next we'll go through some Astro Images. So Steve, are you on the line?
No, I'm actually here.
Oh, there you are. I'm
So
sorry.
many Steves.
I don't drive a type a lot, so, but I had to come out tonight to talk to Chris, so, one of the advantages of observing the planets is that you can work through these cloudy nights that we have. And last night was a pretty nice night, except for all the clouds that came and went. But Mars seemed to stay in a pretty clear area through most of the night. So for 3 hours, I was able to get out there and get images. Now, I didn't stay out the whole time, not at 20 degrees. But I took a series of frames for about, I think it was 60 seconds. For a couple of thousand frames every half hour or so. And you can see how Mars is rotated. You can see the North Polar Cap that Jim talked about earlier. Down there at the bottom of the first image is Sinus Meridiani, and then over on the left-hand side are the big plains of Chryse and Tharsis. And you can see them rotating around the planet in those 3 hours.
Awesome. I think you've told me this before, but your scope is peer mounted, right? You don't have to drag a C14 out when your telescope is peer mounted somewhere.
Oh, yeah.
You
Yeah,
don't
I
have
have a dome in my backyard.
Nice. Nice. That's amazing.
Yeah,
The other thing,
I can get set up and be observing in about 5 minutes,
that's,
but that sometimes is still not enough time, and I'll look out and discover the sky is half clouded over by the time I've gotten started.
I'm jealous because I have to lug my telescope out every time. And here, this is with my C11, this is my image, my contribution this month. This is back from last month when we had the occultation of Mars with the moon or everybody else processes their data faster than me, so I didn't get mine done till now. But what I also did that night was I took pictures of the other, it was the quote unquote planetary parade. So I took pictures of the other planets, except for Saturn, because I got out a little late, later, it was too low, and the scene was terrible that particular night. So I'm amazed I got anything to come out. But what I did here with this image was I scaled the images. I cropped them with the same pixel count on my camera so that these are all really to scale. So you can get a sense. We saw that earlier in Reza's talk with Earth and Jupiter, but here's Mars, relative to Jupiter, and Uranus and Neptune too. And you'll notice my Neptune is bigger than my Uranus, and that's not right. And it's because it was dimmer and I had to take longer exposures on my, the seeing was so bad that my longer exposure resulted in a bigger fuzzball. I didn't do any processing on Uranus and Neptune. Maybe I can talk to some. I don't know if there is any lucky imaging you can do with those guys, but I didn't do that. But anyways,
you need a pretty large scope for getting anything on those. Somebody in the chat asked what your setup was.
it's an 11-inch Celestron SCT, regular, not HD, with a prime focus camera and a 3x power mate, and then just a planetary camera, RGB color planetary camera. Okay, so next, our planetary imager extraordinaire, Jim.
So basically, there was actually one night in January where the seeing was fairly decent. It was amazing. Couldn't believe it. So I did Jupiter for several hours, and these are two of the more interesting shots. This was on the left, of course, the iconic great red spot crossing the meridian there. And you can see a bunch of white ovals for the most part. Those are long enduring storms. Some of these have been around, we always talk about the great red spot, but some of these have been around for like decades. So it's amazing, the dynamics on that planet, that these storms will persist for that length of time. And then actually the one you can see on the right-hand side, there's like two in the north equatorial belt there, one at the top and one below the belt. The one below the belt actually is kind of like, would be almost a Jovian thunderstorm, which is kind of cool, an upwelling. That one probably wouldn't last. The others do. And then on the right side is this North Tropical Zone eruption. It happened, I guess, a couple weeks before. And all of a sudden, this huge upwelling out of the jet stream there, and it's very, very bright white, and it's leaving a train of like dark material behind it. So that's kind of like, and it's moving very quickly. And when I say that, I mean, it's like moving to the right along the belt. So just again, Jupiter is just such a fascinating planet because there's always some cool stuff going on with it.
So it's moving faster than the belt is moving as it rotates, you mean?
Yes. So in other words, if you were to come back like maybe a week later, that white spot might be like almost towards the limb there.
Huh, cool. Okay, thanks. That's awesome. Next we have Joel. Are you on?
Hey there. Hold on, I'm coming. Yeah, took this picture the other night from 18 degrees north latitude from my balcony where I'm standing right now in Punta Cana. The Eta Carina Nebula, also C92. This is with the C star, very little, I just did a little bit in the iPad as far as increasing saturation in the black point, but otherwise no other processing, and let the C star do the stacking. And that was about 10 degrees above the horizon for about 3 hours.
Wow. Neat.
Yeah.
Thanks.
Thank you.
Are you gonna leave your southern latitudes soon? Huh?
I'll be back the end of April. I think I'm hosting May 3rd, our public star party.
Okay, great. Well, keep taking southern hemisphere objects. That's
Yeah.
really cool.
On
Keep an eye on
Monday,
that. Yeah, that star's gonna explode any minute. Keep an eye on it.
yeah, and on Monday I'm heading down to Chile again. I'm not going to the astronomical installations this time, but I'm headed down to Patagonia to do an environmental program down there. So hopefully we'll have some clear skies down there too, because it is like I looked at the light pollution map and there's nothing within like 50 miles. So psyched
Oh,
about.
I was actually gonna put you on the schedule to talk about your Patagonia trip, but maybe we'll do that when you come back and you can
Oh, by all means,
share some pictures.
I'll be in person today.
Harini?
Oh, cool.
The hi, so this is the Pac-Man Nebula. I took it at home with my CSAR S50. I took it for 23 minutes. I changed the contrast and the saturation a bit because I couldn't see the dust and gas very well. And I read about this. It's an emission nebula, and it's made of hydrogen alpha, oxygen, and sulfur 2. And this image was stacked. So
It looks like it says 123 minutes.
yeah, I took it for 123 minutes.
Did you use any special filters on your C-Star when you did this?
Oh no, I just took it regularly, but I couldn't see the gas very well, so I just changed the saturation.
Okay, that's really cool. I think that's a cool one. And in fact, our very next image is Ernie Morse on.
Yeah, I'm here. Can you hear me?
Yes. This
Right,
is
so-
the same object.
Yeah, so I took this with my Vaonis Vespera 2 on impromptu on January 27th at Alpha Ridge, and processed it myself in Affinity Photo from the TIFF file. It's 659 10-second sub-exposures, which is about 1.8 hours. And I would have done longer, but the Vespera, I lost connection to my dew heater sensor, and so it was cold that night, and I was concerned about frost building up on the filter, which was a dual band H alpha and O3.
I remember you calling that star party and thinking you were very brave for going out there.
Oh, this one was Wayne's. This was in late January and before my first one, just 2 days before that.
Oh, okay.
And
oh, right, Wayne's, right.
yeah. So it's been cold a lot, so easy mistake to make.
Can you add to this later with your Vespera? Do you?
Yes, so I can. This one I did set up as a multi-night. I haven't returned to it yet.
Cool.
Cassiopeia is getting a little bit low, but I could always go and add more to it. And I have fixed the dew heater sensor. I just needed to be pushed in much harder, and it's been working since then.
And here's another one of yours.
Yeah, so this one I took actually a little further back in 3 consecutive impromptus, November 29th, 30th, and December 2nd. And it's the IC 1396, which contains the Elephant Trunk Nebula, which is that little thing coming in from the right there as star formation region. And there are a lot of Barnard dark nebulae in here as well. And the cluster in the middle is Trumpler 37, which I observed visually at the same time. I couldn't see any of the nebulosity. The brighter star there just to the left at the end of the elephant trunk is actually a triple Struve 2816, a really nice triple there. The separations are 12 and 20 arc seconds. Can't resolve that here, but if you zoom it way up, you can kind of see it looks like a 3-lobed star with no separation. And the bright star at the top is Herschel's Garnet star, Mu Cephei, which is 4th magnitude and one of the redder carbon stars you can observe. I think that's about the same instrument, same filter.
Anybody home?
We've lost the audio,
We've
guys.
lost the audio from Robinson.
Can you hear me now?
Okay, yeah, now we
Okay,
can.
So where you see the goldish tints and the fluffiness down just left of center at the bottom and a couple places up in the Dolphin Head Nebula itself, that's the hydrogen alpha. The rest of it is oxygen 3. The oxygen 3 was so bright that I use that for the luminance in that image. About 7 hours of exposure. And Dolphin Head is located in Canis Major.
Well, I've seen plenty of pictures of this is the most dolphin-y looking one that I've ever seen. I mean, you can almost like see his eyes over there, and I think it's because you were on the beach when you took this picture. It's an amazing photo.
That's a stunning image, absolutely stunning.
Yeah. Yeah, we're not worthy.
I can't believe I can do it.
Yeah. Well, that is all that we have. So, and I feel good about leaving the Robinson, not making the people stay later than when they're supposed to close at 9. So I would like to thank everybody. There seems to be quite a few people online. I would like to thank you guys so much for attending. Stay tuned for the new website. I think we're going to send a global email out to everybody whose email address is on the list. And other than that, I wish you all clear skies and look forward to seeing you at a HAL event and at next month's meeting. So thanks for joining.
Thank you very much.
Thanks, Victor.
Bye.
Great.
Don't forget to stop recording.
Thanks for staying, Reza.
Yeah, thank you for having me.
Yeah, thank you so much. Glad to have you
Funding?
back.
Oh,
And,
So every year on Valentine's Day,
You need to
NASA
stop the
releases its
recording.
roses call where we find out like